All right, so let's take a look at a distributed load and figure out what that means. So imagine you had a structure, beam, that sits right here. It is constrained so that this point of the beam will not move that way or up. And it's sitting on a roller over here. So this part of the beam can move that way, but it cannot move up. And let's say we started stacking some bricks on it. So we stacked a bunch of bricks across here. All the bricks weighed the same. And then we stacked a row that's maybe, well, let's just stack a row. Stack a whole bunch of bricks. We've stacked a whole bunch of bricks here. And let's say the bricks are such that for a given every foot of the brick, let's say we stacked them so that, we had a bunch of bricks for every foot of width. It says it was 100 pounds. Let's say it was 100 pounds. So let's say this is a 10-foot beam all the way from one end to the other. And we're stacking these 1 foot for a grand total. Well, let's make it on this end. So we've stacked all these bricks, and what you end up with is for 100 pounds for every running foot. The foot's running this way or that way. So now let's think of it like this. Break that force down and say, what equivalent, here we have used the magic of the what equivalent force, so let's say we had an equivalent situation here. Okay, so I want these two situations to be equivalent. I don't know why that's not working. I have no idea what's going on here. Okay. Apparently I can't change colors for some reason. I don't know what's going on. Still green, but we'll work our way through it. Glitch. So these are both equivalent. We want them to behave equivalent. So what does that mean? That means that I want the reactions to be the same. Let's see what happens. It's bugging me now. So I'm going to pause the video and see if I can resolve this ink thing. Not sure exactly what that was about, but I think I got it resolved. So we want these two to be exactly equivalent. So the question is what would this force be, and how far over from, say, the left would this distance be such that this load right here, imagine it like this. You got reaction on the left, and you've got a reaction on the right. They have to be the same. For this to be equivalent, they have to be the same. Well, thing I need to know is how far is this? In this particular case, I'll say it's 5 foot. So it's pretty much clear. I've got 5 foot, I've got 100 pounds per foot, so my value should be 500 pounds. So I just stack it. I mean, that makes perfect sense, but let's look mathematically at what that means. So let's say you had a function This is y. This is x. This function is 100 here. It goes 5. So turns out this 100 is 100 pounds per foot, and that is foot. So as it turns out, it's not too outside the ordinary. That's in fact the area. How do you get the area? So let's call this f of x. Zero to 5. Well, if this is f of x, well, I'll just replace that with the function that's 100, integrated 100 times x, evaluated from 0 to 5, and then in fact, that's what I get, 500. Now the question is, how do I determine where the equivalent part of that load is? Well, there's something that is usually called a centroid, or the center of the area that will get us there. Now, why is that way? Well, let's take a look at it like this. Let's make this 5. Let's say you take one sliver of this, call it dx, and so the weight of this thing is equal to 100 times dx, or it's equal to the function that is f of x dx, or sometimes it's just called y dx. But the key is this creates a moment. Remember what we're trying to do. We're trying to make an equivalent load being 500 at an equivalent distance. So guess what? This thing creates a moment of d times 500 about this point, the origin. So we want these two to be equivalent. Well, how do we make those equivalent? Well, take a look at this. This little sliver, if we zoom in on it, it has a weight to it, and that weight goes straight down, and like we said, that weight is equal to, we'll just call it y x dx. But the key is, it's a distance x from this. So this little sliver creates a moment like that. So what do? We write down the little moment. D moment equals to x times whatever the function is. What we'll do is call it, I'll go back to calling it the f of x dx, because I don't want to get things confused there. So there's a function here. That function in this case just happens to be straight line. Sorry, took a pause there for a second. So this little sliver creates a moment. So what we do is we integrate or add up all the moments, and we get the moment from this entire distributed load across the whole thing. As it turns out, not too bad of a deal here, because in this particular case, x times 100 dx, and what we end up with is 100 x squared over 2, evaluated from 0 to 5, or 125 over 2 Now, if you look over here, this thing, okay, so remember what we're trying to do here. We're trying to make this equivalent to that. And if we can accomplish that, then we will have the correct load, 500 pounds, distributed at a certain distance that makes these moments equal. So at this point, I'm thinking about just leaving this as a 50, take the 2 off here, times a 25 equals D times 500, which gives me D of, let's see, oh, got to take a break again. Okay, I'm working on a shortcut key, and it seems to work. Okay, I'm really sorry about taking the delay there. Okay, so you got 50 times 25 over 500, which gives me, take away 1 0, then 0, then a 5 and a 5, gives me 25 over 10, or 2.5 is equal to D. So I'm sorry, in the early stages of these videos I'm bouncing back and forth a little bit. So, but the key here is that in fact we did find an equivalent load here. Equivalent load is 500 pounds located at 2.5 feet over to the right. This load and this will give me the same reactions here and the same reactions here. So let's take this a step further. If this is a general form that works, and it should, let's try to find something else. Let's take a beam that is, and you know what? I think sometime I was told, yeah, here we go. So let's say we had a beam that's that long. This time, well, I tell you what, if I'm using a straight edge, let's just use the straight edge. Let's say the load was out here. Very annoying. There we go. So that you've got a triangular load this time. So the key is how far did it go? Well, this went out here to say 200 pounds per running foot. Now what this is, let's just imagine we did this. Stack a couple of bricks like this, and we're stacking bricks like so, so that each of the bricks are the same, but essentially you're stacking more and more bricks out here to the right. So what you're looking at is an increasing load where you're stacking more and more bricks higher to the right. Gives you that triangular look. And I hope what I just explained made sense. But the key is, let's look at the function. What is this function? Let's say this is X. You've got your support reaction at the left, reaction at the right, and your function starts here. Here's your Y. It's just 200. Let's say this is 5 foot again. This is the rise over the run, 200 over 5 times X. Now you don't have a constant load. Okay, the intercept is right there. So let's first find the equivalent weight. We integrate f of x dx, what we were talking about right back here. And then let's put this in. And we're going from 0 to 5. We're integrating. What's 200 divided by 5? 100 divided by 5 is 20. So this would be 40 x dx. So we integrate this thing. We get 40x squared over 2, evaluated from here to there. What we end up with is 40 times 25 over 2, or the equivalent of, let's see, 40 times 25 divided by 2 gives about 500 pounds. Now, let's look at it for the mathematical sense of what this actually means. If you've got a function that sits here, it's 200 high, it's 5, and you want to know the area, your area is equal to 5 times 200, and you're missing half of it because the area is does not include this upper part. It only includes this lower part. So what you end up with is 200 times 5 is 1,000, then half that's 500. That's exactly what you got over here. Let's make sure I'm still recording. Yep, still recording. So now we want to find the equivalent moment, the equivalent location of the load. Where's the load supposed to be equivalent? Is it 500 pounds over here? Is it 500 pounds here? Well, let's just follow exactly what we did before. We know we found 500 pounds. Oh no, now I can't change pins again. For some reason, when I step back down, I can change pins or cannot change pins. Okay, I'm going to have to pause it again. Okay, it has something to do with the interaction between these two pieces of software. I don't know. So let's integrate. Can I change the pin? Yes. Integrate from 0 to 5 of x times f of x, and that's equal to the moment. Well, the equivalent moment, okay, so if I take this beam and I move it over here, and I'm wanting to find the equivalent moment, that equivalent moment is a force, which actually happens to be 500 pounds, times the distance. So that's got to be, okay, dx is equal to the distance times the 500, or the area, or in the book, some books it'll be written like this: integral 0 to 5 f of x dx, where in fact that is the 500. So you just carry it out, and what you get, 0 to 5 x f of x. In our particular case, it's 40x dx. Now you might as well get rid of one of the x's and square it. So you got 40 x to the third over 3 evaluated between 0 and 5. And so that's 40 times 5 to the third over 3. Okay. And that's still got to be equal to 500 times the distance from this and so my distance is going to be equal to, okay, let me figure all this up on the calculator. So I'm going to pause and do this real quick. Is equals to 3 1/3. So, as it turns out, in a standard sort of sense, always the way this works is this. Let me bring my ruler back up. If I have a triangular load, then what we're looking at is whatever this length is here, the centroid, which is the location, which is what we're ended up finding of this area, is L over 3 from the heavy end, or 2L over 3 from the light end. Turns out 2 times 5 over 3 becomes 3 1/3. This is always the case. How prevalent? Well, let's take a look. Let's see if I can get myself to, oh shoot. Okay, what I wanted to get to was this gentleman's website here. Okay, let's look at these tables. The area, there's a right triangle. There's a non-right triangle, but we're looking at a right triangle. What you'll find is the point in the center is the centroid. So if this was an equivalent load, then that would be the centroid of it. 1/3, or B to the third from the heavy end, H to the third from this end. So let's say this is a homogeneous plate and you're trying to balance it. You would have to put your finger right there to balance this plate. If you put your finger over here, it would fall off your finger. So in fact, this is the same kind of concept that we've got going here. You've just found the equivalent load. It's like placing a bunch of bricks on here. You found the equivalent location of that load. So I hope this was useful. This may be a supplement to what he's done. He's done a very good job of it. And I'll go ahead and post this now.